We have been talking about kind of the limits of computation using Turing machines. Anybody been thinking all weekend about uncomputable things? Anybody got any deep thoughts to offer? I tried to offer my sort of half-baked deep thoughts. I don't know if anybody has any similar deep thoughts. No? All right. That's all right. Okay, what I want to talk about for our remaining time together, that is today and next time, is two examples of uncomputable things. They are omega and what's called the PCP. That's a something called the post-correspondence problem, which I will say more about. Omega, I gave you a little introduction to last time, and we can talk about some more details here. This is called chitin, I think is how you pronounce this. This is a Russian name, but I don't believe it's pronounced like a ch. Anyway, chitin's constant. This is also known as the halting probability. If you don't want to embarrass yourself by saying the name wrong, you can call it the halting probability. It is a number, a specific number, which is why I called it a constant. And it's a number between 0 and 1 because it represents a probability. And this is an example of an uncomputable number. I mentioned this sort of at the end last time. It is a fact that this is a specific number, which definitely does exist, but its digits cannot be computed by any Turing machine, which basically means that we human beings have no way of actually calculating the digits of this number, even though we can prove abstractly that it is a real number and it really does exist. Here's how this is defined. So the halting probability is defined like this. Now I'm going to give a specific definition using the programming language Python. You can give a similar definition using any formal programming language, but it is about kind of programming languages. So I'm going to say with Python, it's the same thing using other languages, although the actual value of this constant depends on what language you're using to begin with. Like the value of the halting probability for Python is different from the halting probability for JavaScript, just because of the way the languages are slightly different, even though they do all the same stuff. Anyway, here's the idea. So I'm going to say, I'm going to define, first of all, a function that goes from the natural numbers to the real interval 0 to 1. And this is defined by f of n is the, I'll write it in words first, and then I'll write something slightly more specific. It's the proportion of all random strings of length. Can I just take out that word random? I just mean it's the proportion of all strings of length n which represent legal Python programs that halt. Right? Of course, when you write a program in Python and run it, sometimes it halts and sometimes it doesn't. Like, if it's a useful program, it probably halts, because that's what most programs are supposed to do. This f of n represents the proportion of all strings of length n, which represent legal Python programs. This, as a proportion, is very, very small. I'm just saying, if you give me a random string of length n, what's the proportion of those which are legal Python programs when you try to run them? The answer is almost none of them are legal Python programs. If you just give me a random string, it's just a bunch of nonsense, probably. Although some of them, by some ridiculous, sort of infinite, monkeys with typewriters kind of idea, some of them are legal Python programs. For instance, one which begins with the, some of them are just all comments in Python, right? You do a comment in Python with the hashtag, right? Is that right? Or is it the slashes? I get them mixed up. The hashtag, right? So at least some of these, if you give me a random string, there's some chance that it starts with the hashtag, and then it is legal as a program. It doesn't do anything, but at least it's legal, right? And that one halts, okay? So anyway, you could write this in more detailed way as a fraction. This is the number of halting programs of length n divided by just the total number of all strings of length n. All right? And this fraction is very close to 0, but not equal to 0, because there is some small chance that you will, that those strings are actually legal Python programs. So f of n is close to 0, but not equal to 0. Well, can I just say f of n, it's greater than 0, but very small, right? And what's the definition of the halting probability? So this is basically what I mean when I say halting probability. It means sort of like if I just give you a random string, what's the likelihood that it represents a Python program that halts? And the answer is pretty close to 0, but not exactly equal to 0. There's some probability of that. All right. The definition then of the constant as a specific number. Each of these. There's like different ones for every possible length that you could consider. The total, the constant is defined in this way: lim n goes to infinity of that. So this, you should imagine this. Since I'm doing this limit, this is kind of like if I were to say this in colloquial language to my buddies at lunch or something. This is like the probability if we take a random, very long string. The probability that if we take a random, very long string, that it is a legal halting Python program. That's how I would describe this in words to my mom, say. My mom was a career computer programmer, so she would know what I was talking about. She would say, wait a minute, that's not even a computable number. My mom probably would not say that. I don't think she ever learned about the abstract theory of computation, but maybe she did, I don't know. My mom's done a lot in her life. All right, we don't need to talk anymore about my mom. Come by my office, you'll see there's a quilt on the wall right in the hallway outside my office, made by my mom. Check it out. Anyway, it's a mathematically interesting quilt. This is the probability that if we take a very long string, then it is a legal halting Python program. Now, I would like to consider what would it take to actually calculate this number. In order to calculate that number, you need to be able to analyze all the strings and then see which of them represents a program that halts. And this is a major problem if you're trying to actually calculate this. So we already know it is impossible. This is what we talked about last time, the halting problem. It says that it is impossible for any algorithm to decide in general which programs halt or do not halt. Right? It is impossible for any algorithm to decide in general which programs halt or not. What that means is it is impossible to calculate this number. In particular, it's actually impossible to calculate this complete sequence of fn's. You might be able to calculate, say, f of 1 is not so hard to calculate. That's just like if I have a string of length 1, what's the chances that that string by itself represents a legal Python program? And I don't think just like a single character is a legal Python program all by itself. I don't think it is. You have to have like an equal sign or something. Although if it were a hashtag, that would be legal. But anyway, you can calculate some of these when the n is small, but you cannot ever calculate this because it would require some general purpose method by which you could tell if these programs halt or not, and that is impossible. So it's impossible for any algorithm to decide in general which programs halt or not, and what that means is, so no algorithm can calculate, in particular, you can't calculate the digits of omega, all right? You may be able to calculate some of them. Yeah, that's the question.
Could you approximate it?
Yes, you absolutely could approximate it. For example, I'm about to. It is approximately 0. It's true. And so if you calculate it as a number, as a decimal number, it's in this range. It is between 0 and 1. And so I could say it's probably, 0.000 something, maybe even more zeros. So you can try to approximate it. If you really wanted to do a good job of approximating it, you would start by considering all possible strings, say, of length 2. How many of those halt? And then all possible strings of length 3. How many of those halt? And you could, in theory, continue to do that for as long as you're able. But because the halting problem is unsolvable, it means there's no general way to calculate all of those digits, right? So no algorithm can calculate the digits of omega. It is an uncomputable number. That's what we say. Omega is an uncomputable number. Right? It is a real number, which you can prove exists. I don't know if anybody is concerned about this, but you may have asked up here, I said this, right? How do we know that the limit exists? Of course, that's always an option when you're talking about limits. Maybe the limit does not exist, and then nothing that I say matters at all if this limit doesn't exist. But actually, the limit does exist. There's a theorem from in your Calc 2 class when you learned about sequences. There's a theorem called the monotone convergence theorem that says if a sequence is monotone, that is either always increasing or always decreasing and bounded, then it automatically converges. This sequence is bounded below by 0, and it is decreasing. That's because if you take an even longer random string, it's even less likely that it becomes a valid program. And so this sequence is decreasing, but always greater than 0, and so it does converge to something. All right. That means, if you want to have deep thoughts about this, you could ask your friends. Do you think no human being can know all the digits of omega? Do you think God could calculate the digits of omega, or do you think that God knows the digits of omega? I would say, the answer is something like, well, maybe God knows them just by the definition of God or whatever, but I don't think that God can calculate them by an algorithm, and I don't know if this is saying something about God having a weakness or something. I don't think it really is, but there isn't an algorithm that can do this. If God knows the digits, it has to be because of some kind of miracle, not because of, he did it using an algorithm. All right. I actually was thinking about this over the weekend. For some reason, the question occurred to me, if I want to say something like, well, yeah, God could know the digits of this constant, but he can't. But God can't do it using an algorithm. And is that somehow a weakness of God? It made me wonder, something like, okay, in the universe of Christianity, Jesus could walk on water by performing a miracle, right? But you could ask, okay, but could Jesus walk on water without using miracles? Huh? And my answer is I guess not. I don't know. This is a weird question, but it's a similar question to could God calculate the digits of omega using a Turing machine? No, but without using Turing machine, maybe? I don't know. These are weird questions that I think about sometimes. Any thoughts about that? Could Jesus walk on water without performing a miracle? I don't know. You could ask, could Jesus be infinitely strong? Could he lift up a car? Yeah, sure. Okay, but could he lift up a car without using his Jesus powers? I guess not. I don't know. Does that mean that he was really weak? I don't know. These are the kinds of things that I think about from time to time. All right. Very interesting, in my opinion, that there are numbers like this, though. So put that in your sort of batch of fun facts about mathematics in general. In fact, I'll go one better. Actually, if you have taken our real analysis class, and maybe in our discrete math you may have talked about this, there are different sizes of infinity, and there's sort of a small size of infinity called countable infinity, and then there are larger sizes of infinity called uncountable infinity. Have you all heard of this? No, I know some of you have at least. Anyway, it turns out that the numbers which are computable, those numbers for which you actually can calculate their digits, will be things like all the rational numbers you certainly can, but also things like pi or square roots or whatever. Those actually are a small proportion of all the real numbers in general. So I will just say, turns out, and I don't want to get into this, but it's a true fact, almost all real numbers are uncomputable. Like, this is one example of an uncomputable number. You might wonder, like, are there others? The answer is yes, there are many, many others. And in fact, real numbers, generally speaking, most of them are not computable. The ones which are computable are like the rational numbers or the whole numbers or other types of numbers. Actually, the larger set of numbers would be the ones which are uncomputable. Strange but true fact about the real numbers. Now, so this is the omega. I want to talk a little bit about the PCP. That was the other thing that I wanted to discuss. So there are uncomputable numbers, such as the omega. There are also sort of uncomputable calculations. That is to say, there are certain problems where I could give you like a problem for you to solve, and it turns out that problem is just impossible to solve using any algorithm. And one example of these, so one example is the halting problem. This is the example that we talked about last time. This has to do with, if I show you a program, can you tell me whether or not it's going to halt? You may be able to do that in specific examples, but in general, there is no general purpose procedure which can do that. All right. This is a little unsatisfying, though. What I said last time was it's a little unsatisfying if all of the examples have to do with this halting, and this omega number also has to do with the same kind of halting thing. These are all kind of far out, but I have another example which doesn't actually, on its surface, it doesn't seem to have anything to do with halting or other programs or Turing machines or anything like that. So another example is called the post-correspondence problem. Post-correspondence problem. And this is, I'm going to write this as PCP. The post-correspondence problem. Post is the name of a person. Emil Post, one of the old school OG computer scientists. Post apparently is the person who invented the word string as is used typically in computer science, which I think is some kind of great achievement, I suppose. Post also came up with the post-correspondence problem. So this is from 1946. He proved, or he wrote a paper about this problem. This is pretty recent, like pretty close in time after Turing's original work. And this is invented as a normal seeming problem, which ends up being uncomputable. And here it is. I will describe to you. It's kind of like a cute little puzzle, all right? Something like given blocks like this. Let's say I'm going to write 4 different tiles, and they are labeled, each tile has a string on the top and the bottom. And I'm copying this very carefully from my paper here. 4. I want 5 zeros at the bottom of this one. All right, and this one has some kind of special special business around it. All right. So you have 4 blocks here, and you could imagine if you like had these on little cards or something in real life. It's a puzzle about rearranging the blocks in a certain way. And the question is, so this fancy looking one, this is called the starting block, or the starting tile. I'll call them tiles. This is called the starting tile. And the question is, can we arrange them in some order? You can put them in whatever order you want, although you got to start with the starting tile. Can we arrange them starting with the starting tile? And repeating them if you want to. So the idea is to make some arrangement, and you're allowed to reuse them as many times as you like. Repeating if you like. And the game is, can we arrange them starting with the starting tile, repeating if you like, so that, here's what you want. The goal is that the full string that you read across the top, you imagine you're going to kind of line them up, right? So that the full string across the top equals the string across the bottom. This is your job. The question is, first of all, is it possible? And then, if it really is possible, then can you say how to arrange them? You got an answer?
It has to start with, the same first digit, right?
Yeah, so in order for this to be possible at all, the starting tile has to have some kind of regularity to it. Is that what you meant?
Yeah.
Yeah, right. So in this case, it is true that the top and the bottom of the starting tile are already sort of matching up, so that's how you get yourself started. Can anybody see how to do it in this example here? I thought about making cute little cards, and we could all, play with our little PCP cards, show them to your friends. Yeah? You gotta start with the start tile.
All of them?
You don't have to use all of them, and you can repeat them if you want to.
So I did the starting one, the first one, and then the last one.
Okay. What'd you say next?
The first one, 0.
Oh, all right, I see. 0, 101. Can you say anything about why you chose that one next?
Because the bottom, it adds on to it to complete it's now accurate with the starting one, and now we only have the 0 as the difference.
Right. So there are actually some strategies that you can deduce, right? I have to start with this one, all right? And then the fact that I eventually want the whole top to be the same as the whole bottom. That means what comes next down in the bottom must actually be 101. Or it could be, it has to start with a 1 at least, right? It doesn't have to actually be all 3 of the 101s, but the next tile that you put on the bottom better start with a 1. So now it says 10101, which matches so far, although I'm not done yet because there's an extra 0 here. And what else did you say?
And then the last one.
Yeah, and then the last one, 101. Yeah. So this way, if I put them in that order, then the top string is 1010101, and the bottom string is 1010101, like that. And they are the same, so this is a valid solution to the problem. All right? So the question in the post-correspondence problem is, if I show you the tiles, can you produce for me an answer like this? Or maybe, in some examples it's not possible to do, and in those cases you should just say it's not possible this time. Right? This is called the post-correspondence problem. Post, in his big paper in the 40s, Post showed that PCP is unsolvable by any algorithm. All right. This is a problem. This is something that is kind of interesting to me in that I can imagine, writing like an iPad app, a little game where you do this, right? Although what I'm saying here kind of means that you can't do this with a computer somehow. Anyone want to say, what does it actually mean? I say it's unsolvable by any algorithm, but he just solved this one. So what What actually does it mean to say it's unsolvable when we actually just solved it right here? Can anyone say more? Yeah?
You won't know if it's possible. Like if an algorithm, like obviously it's possible there, but if it's impossible, it'll keep going.
Yeah, right. The thing is, like in this particular example, maybe it is possible and maybe it's not. And in any specific example, it is possible, probably, to either solve it or somehow argue, demonstrate that it's not solvable. But the problem is, if there can be no general purpose procedure which will be able to solve any example that I can come up with, all right? So it means, like, I could actually make a little, iPad game or something which spits out random collections of these and then asks the player to either solve it or say that it's impossible. Although I guess what I would say is it's not, like you could make an iPad app that does that, but actually the app itself would not be able to ever know for sure if the examples it's generating are solvable or not, because the app itself is not capable of ever deciding for any given example. It might not be able to decide if it's solvable or not. All right, this is unsolvable by any algorithm, and this is so. Post did this by showing that, and this is the lingo that they use in this business. Post did it by reduction to the halting problem. That is to say, specifically, Post showed how if you somehow had some kind of magical procedure for solving any PCP, that same procedure could be kind of reworked into a general solver for the halting problem. And this is actually, Post's detailed argument is pretty interesting, and it is something that I would like to go through in detail. Not in complete detail, but I want to do a specific example. Although I think it may take more than 10 minutes. So maybe I'll leave that for, we got 20 minutes? I'll leave that for next time. But I would like to say, so we'll do this next time, the details here, because I think it's interesting. But before I say, I just wanted to say nowadays, so now, 80 years after this, we now understand that we know that many problems are just straight up unsolvable. Uncomputable, I will say. And this is now regarded as like a legal way of answering a mathematical question. Of course, people doing math research today are trying to solve a bunch of problems. It turns out some problems just straight up are not solvable, and often the resolution to these questions is when somebody proves that this question is unsolvable. So, and I actually had an experience where some of the research that I was doing in my when I was getting my PhD, some of the research I was doing in my dissertation, I was working for years trying to solve this particular problem, and then I got an email once from somebody who said, your problem in certain cases is equivalent to the post-correspondence problem. And I thought, when I read this email, I thought, this is good news. If my problem is equivalent to something else which already has a name, then that probably means I can go read about that other thing. At this time, I did not know what the post-correspondence problem was. And then I learned this is very bad news. It means if my problem is actually equivalent to the PCP, it means there's a reason I've been working fruitlessly for years on it. It's because it's actually provably unsolvable. My problem only in very specific situation is equivalent to the PCP. So it wasn't actually a real bad news for me. But I'm just saying, these days when mathematicians are working on problems like this, one resolution is to actually solve the problem. Another resolution sometimes is you end up demonstrating that the problem is unsolvable. Yeah.
What was your problem?
It was a problem in group theory. It's a little hard. It's called the doubly twisted conjugacy problem. It's a little hard to explain. I could explain it, but then you would ask me, why does anybody care about that? And then I would have a hard time without giving like another couple hours of explanation. So it's a super abstract thing. But it's like when you're working on math problems, I mean, like as a student, whenever your professor asks you to do something, you sort of have faith that it is possible to do it. And so you never really grapple over this question. But working mathematicians, this is always something that's like in the back of our mind. Maybe this thing I'm trying to do, maybe I just can't figure it out because I'm too stupid. And that's usually the case. But maybe, just maybe, I can't figure it out because it's impossible to figure out. Then I would like feel better about myself, I guess, for not having figured it out. Many problems are uncomputable. And there are, like, in terms of the big unsolved problems of today, you know, there are problems called the Millennium Prize problems, which have $1 million prize associated to them. To get the $1 million, most of them are like theorems. You can either prove they are true or prove that they are false. But actually, part of the prize, like, it is acceptable if you prove that one of these things is impossible to do or impossible to answer. That's another possible resolution also. I just thought I'd give you one example, another important example. And I think I'll leave you with this just because we're not going to fill all of our time next time, so we might as well not milk it today. An important example is called the Diophantine polynomials, and it is, this was something that was regarded as an unsolved problem at the beginning of the 20th century, and it is now sort of, in quotes, solved because people proved that it's impossible to solve. But the question is just, given a polynomial, you know, ax to the n, I'll say an plus blah, 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 a1 x to the 1 plus a0, something like that. Does a root exist in the integers? Right? Every polynomial has real valued roots, at least in the complex numbers, but this is about asking if you can solve a polynomial using a whole number as a solution. Does it have a whole number solution? This doesn't seem to be about anything having to do with Turing machines or halting or whatever, but actually it has now been demonstrated that if you are capable of answering this question in all cases, that could somehow be reworked. That strategy could be reworked into a general strategy for solving the halting problem, which we know is impossible. Most of these things are shown to be unsolvable by translating them into the halting problem. All right, so my agenda for next time is talk specifically about the PCP because I think it's interesting, and then most of our time we'll spend just talking about the test.